Okay, so I did start to cover this in our lecture, but I couldn't finish it. So here is a short version of covering all of these cache related questions that are important for the final. So first off, let us look at some of the basics. So any cache, the size has to be uh, 2 to the power n. So the size can be either 1, 2, 4, 8, and so on. And let's say you're given a question that you have block size of one word. Now, we know one word is 4 bytes, right? And you are given that the cache size is 32 bytes. So then how many cache entries do you have? So, so you have one block, which is 4 bytes. So 4 bytes is one block, which is one cache entry. So if you can have, with 4 bytes, you can have one cache entry. With 32 bytes, you can have 32 divided by 4, that is 8 cache entries. Now, because with 32 bytes, you have 8 cache entries, you need some index to point at a specific cache entry. So if you have 8 cache entries, what should be the binary bits you need to represent one cache entry? So we all know that with 2 bytes, with 2 bits, you can, with 00, 01, 10, 11, with 2 bits, you can point at 4 different entries. So it's basically 2 to the power n is equals to 8, and here n is the number of index, like index bits you need to represent this cache entries. So you can find that n is equals to 3. So your cache index needs to be 3 bits in size. Okay. Now, this is for your normal direct mapped cache, but you can also have n-way caches. With n-way caches, it means that, like, if it's a two-way cache, then in one set, here the entries you have are sets. So in one set, you can have 2 blocks. So if you are asked the question that you have a 32 byte 32 byte is your cache size, right? So if the cache size is 32 bytes and the block size is 4 bytes, and it's a two-way set associative algorithm that we are following, then how many set indexes do we need? So here the question mentioned that the block size is 4 bytes. Okay, let me just so block size 4 bytes means in one location it can hold 4 bytes. And then it said it's a two-way. So in each entry, you can have 2 4-byte locations. So with one set, you have 8 bytes. And then the question is, how many sets can you have? So basically, if you have with 8 bytes, you have one set. Then in 32 bytes, you can have 4 sets. Now, uh, so how many set index do you need? So how many bits do you need to point at 4 locations? We know this, it's 2. But here's another question. The question is that, like, we know that addresses are byte addressable in MIPS, right? So apart from this, because this is 4 bytes, you also need 2 to the power n, 2 to the power n equal to 4. You when you access one memory location, you also bring in its buddies. So you need a way to point at its buddies too. So because this is 4 bytes, you need 2 bits to point at its buddies. So 2 bits to point at its buddies, and 2 bits because uh, 2 bits to point at its set, because we have 4 sets: set 1, set 2, set 3, set 4, right? We have 4 sets, so 2 bits. So set index is 2, and also offset is 2. With the offset, you can point at individual bytes. This will come in handy in the next so this will come in handy in the next questions. Okay. Let's look at the next question. So here, this is a problem. This problem says if you have a fixed number of fixed cache size, if you vary the block size, then how will these things vary? Okay. So that's the question. So let's say you have a block size of 1 byte, right? So if you have 128 bytes, and if each block is 1 byte, then you can have 128 blocks. And then with you can find, if you have 128 locations to point at, what should be like the binary uh, bits you need to point at these 128 locations. It's basically 2 to the power n equals to 128, n equals to 7. Also, you can find this by n equals to log 2 base. If you have the calculator, that is, just quickly find it this way. It will equal to 7. And then you have your set index. So your set index is going to be 7. And because you don't have its buddies, you have 1 byte, right? So you cannot bring in its buddies. So your offset will be 0 in that case, because the memory is byte addressable and you cannot bring in its buddies. So your offset will be 0. But in the second case, we see that what if the block size is 1 word? 1 word means 4 bytes. So for 4 bytes, if you have 128 bytes, you can have 32 blocks, because if 1 block is 4 bytes, then how many blocks can you have with 128 bytes? You can have 32. Now here, another thing is, among this 4 bytes, you have to point at these 4 locations too. So to point at these 4 locations, you need a selector that is 2 bits. So this selector is your offset. And the other thing is you have 32 locations to point at. So to point at these 32 locations, you need 2 to the power n equals to 32. So n equals to 5. So 32 minus 5, that could be our answer, but no, you have to remember that the address in MIPS is byte addressable. So you have to point at those 4 bytes as well. So you need a 2-bit selector to do that. So 27 minus 2, 25 will be our tag number of bits, which is tag. So anything you need to locate a memory, anything you don't need becomes a tag. So you need these values of 4 bits to, no, you need 5 bits in our example to point at the block you want to locate, and within the block you have 4 addresses that you have to point to. So you need an offset of 2 for this example. And everything else, the rest 25 becomes your tag. And if the tag matches, then it's a hit. So if the tag and all, like if the tag match with another memory location, it means when you bring in a tag, you bring in all its buddies too. So that's why it becomes a hit. Because once you bring in this, the result will be within its buddies. So if you bring in a set index and the set index and both the set index and the tag matches, then it's going to be a hit. But remember, both set index and the tag has to match. This will be more clear when we go to the examples. So let us move on. So I'm quickly making space for the next question. So now we can see, what if it's 4 words? 4 words means 4 into 4 equals to 16 bytes. So if you have 16 bytes, then if one block is equal to 16 bytes, then 128 bytes will give you 8 blocks. And you need a selector to select these 8 blocks too. So the selector will be 3 bits. So our set index or our cache index will be 3. But because this is a 16, right? We have 16 bytes to point at. So we need an offset to point at these 16 locations. So 2 to the power n equals to 16, n equals 4. So we need offset size of 4. So our tag size will be 32 minus our cache index size or set index size minus offset size. So 25 will be our tag. Now, let's look at this next question. So, if you have a cache size of 256 bytes and it's a 4-way cache, and with a block size of 1 word. So what this 4-way cache means, in each block, in each entry, you will have 4 blocks, and each block will be 1 word or 4 bytes. 4 bytes, 4 bytes, 4 bytes, 4 bytes. And then, and you call this entry a set entry. So one set equals to 16 bytes. So how many sets will you have? So I have a calculator. So quickly do it. 256 divided by 16 is 16. So here you see a visual representation that we have 16 sets, and each set will have 4 blocks. And can anyone, oh, so there's no students, but uh, we still, even after we identify which set we want to access, we still have to identify the, like, within one block, we have to identify the uh, specific, like within this block, I have to identify each of the byte. So we have 4 bytes in one block. So 2 to the power n equals to 4 and n equals to 2. So we still need a 2-bit selector to select between the values. So the set index is, because it's 16, 2 to the power n equals to 16. So n equals to 4 and our offset equals to 2, because inside each block, we have to identify each byte as well. And with this, we identify the set. Okay. So now let's move on to the next question. So if we look at this question, first we have to understand which algorithm are we using. So we are using the direct map algorithm, and with direct map algorithm, let's first like clear out the answers so we can do it from scratch.
With LLMs, we can't because they require so much resources to train themselves.
Okay. So for direct map cache, we have an index and we directly put the value in the corresponding index. Will be clear when we solve this. So here we have 7 memory locations. It could be more or less, doesn't matter, but it's an arbitrary number that we have 7 tasks to do here. So, and the cache block size is 1 byte. So immediately we know that, uh, immediately we know that with 1 byte, we can only identify one memory location. We cannot bring in its buddies. Okay. So normally with caching, you bring in the memory you accessed and also bring in the friends of that memory. So the neighboring memory locations. But with 1 byte, you can only bring in that specific value. So that's one thing we have to keep in mind. We have to indicate if it's a hit or a miss. Okay. What the tag value is, assume the cache is initially empty and accesses are in the order of appearance. So how they appear here is the order of access, and you wish to draw the cache. That is helpful if you want to solve the problem. So we drew the cache here, and the memory location are in base 16. So if it starts with 0x, that means it's in base 16. And we have to express the cache index and the tag in binary. So it's easier if you do that in binary because uh, like uh, eventually you have, in order to find the tag and the cache index, you have to convert it into binary. So it's easier if you just put in the value. So with this problem, these binary values won't be given. And if you bring a calculator, you can quickly calculate these binary values. Also, you can use the table, the that table where you have the hexadecimal values. And I think we don't uh, we don't use the octal or the decimal values that much. So I can remove, basically we don't use the octal values. I can, okay, no, you might need it to convert. Okay. So you can use the cheat sheet to find these values, or you can use the calculator to find these binary values. But once you have these values, you have to first find what's the size of the index. So 8 blocks, right? So how many, uh, so 8 entries, you have 8 entries. How many bits do you need to represent 8 entries? That is 2 to the power n equals to 8, and then if n equals 3. So, so the first 3 bits are the index for that, uh, for this problem. Note, we don't have any offsets because we don't have to select between the 1 byte, If it was 4 bytes, then we needed an selector to select between those 4 bytes. So we needed a 2-bit offset. But in this problem, we don't need an offset because the block size is 1 byte. Okay. Now, uh, the thing is, the first location will always be a miss because you haven't started anything. Okay, and you divide the the first 3 bits and you match it here. So 010, the cache index of the first location is 010. And what's the tag? The tag is the remaining portion. So it's easier if you write like this, 0 dot dot dot. So a lot of zeros and then 100. It's, so if the two tags match, then it's a hit. But we have to look at the second one if it's a hit or not. So the cache index, so it's a miss and you put it inside the cache. So we put the first location inside the cache. So here we have put 1 inside the cache. Okay. Now the second location. What about 2? So, for 2, the cache index is also 010. And we have to check if the tag matches. If the tag matches, then it's a hit. But unfortunately, the tag doesn't match and it's 011. So the tags don't match here. So it's going to be a miss. And with direct map values, 010 is only going to be put in this 010 index. So uh, number 2 memory location will replace number 1 memory location. And now let's look at 3. 010. Let's see if the tags match. The tag doesn't match, it's some value. Uh, you have to write it down because it can match with something after it, right? So you have to write down the whole tag. And if you want, you can try to like minimize it by having dot 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 to represent the number of zeros. So I use dot 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 here because there are lots of zeros. You can also do that for number of ones. So instead of writing this, I could have written like could have written could have written 1 dot 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 1, and then I represented 8 ones here, and then 0 0 0 1 0. So okay, so now this doesn't match, so it's a miss. It doesn't match with 2. Remember, 1 has been deleted. Even if it matched with 1, doesn't matter. So 1 has been deleted. Now 2 doesn't match. Like the current value doesn't match, so it's going to be removed, and the next value is going to be put in into this slot, because the cache index determines where the memory gets put in if we are doing the direct map algorithm. So again, this one, it's 100, and it's an easy tag, which is 0 dot dot dot, and there's only 1. Okay, this doesn't match. And 100, it's the first time we have 100, and then this is the 4th instruction we put here, and it's a miss. For the next one, it's let's write the tag. Eventually you have to write the tag, so I'm writing it in the beginning. 1 1 0 1 0 1. It's a miss because so 0 1 0 will replace this 3, but 3 doesn't match with this, right? 3 doesn't match with this one, so 3 has been removed. Now 5 will be put in its place. 5. Okay, now this one 110 hasn't been ever used, so we'll just put the 6th one here because there's no chance of remember, both the cache index and the tag has to match, or else it's not a hit. Okay, so it's a miss. And then the final one is 010 010, and the tag is 0 dot 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 0 1. Now we can see that this actually matches with number of 4. Okay, and but the index doesn't match, so it won't happen. Okay, so it's not a hit because the index has to match and also the tag has to match. So everything is going to be a miss. Another thing you can see is that this 12 and this 12 are the same thing. So basically this and this also match, and also their cache index matches, but it won't help because one has already been removed. That's the problem of direct map, is that if you get a new if you get the same index in another location, then you have to remove the previous location. So if this one had stayed inside, so if this had happened after this, then it would have been a hit, but it didn't, because there were some memory accesses that were made in between, and basically this one got removed in the second memory access. And remember, we don't have offset here because the block size here is 1. Okay, so the block size here is 1. So in order to be a hit, it has to exactly match the value, and also that location has to be inside the current cache. It can be deleted. Okay, so all of them are missed. Now we will look at 2 more problems. So let's look at this problem. So for this problem, it's a two-way cache and 8 sets of cache blocks. Wait, let me remove the solution. So here, the problem states that it's a two-way cache. So with a two-way cache, it means that each set will have 2 blocks, and it had 8 sets. Block size is 4. So it has 8 sets and block size is 4. So this is 4, this is 4. So one set is 8 bits. And we have to do the same thing. And if we are deciding on evicting a block, which block should we evict first? It should be the least recently used. So we'll come back to that when we do have to get rid of blocks. But currently, let's solve this problem. So the first thing you need to do is get the binary values of these memory locations. So once you have that, you need to understand the block size determines the offset. So the block size is 4. So the offset will be, the offset will be 2 to the power n equals 4 and n equals 2. So offset will be 2. So you see the offset 2 here, 2 bits are allocated for the offset. You also have 8 sets. So if you want to point at any of one of the 8 sets, you need a selector that is 3 bits. So n equals 3. So you have a 3-bit set index. Okay. So then you draw this line to separate what's the set index, what is the offset. And now we have to check whether it's a hit or miss. So first location 0010, the set index or the cache index is 100. And what's the tag? The tag is 0, all 0. Oh, nice. And it's a miss because we know first one will definitely be a miss. Second one, the cache index doesn't matches, so it's a miss because we only have this to compare with. Oh, but interestingly, the tag matches, but doesn't matter. Both the tag and the cache has to match in order for it to be a hit. So if you write it like this way in here, then it's easier to copy the tag here as well. So you can do this actually. Put dot dot dot. And
Even if he was like, that's not great.
eliminate the leading ones. You don't have to write it out. Okay, so third one, 110. 110. We also have to put these values in the cache. So 100, we put 1 here, and we put 2 in 111. So we put 2 in 111. And this might confuse you, so I'm just okay, so we are now on the third one. Third one is 110. So third one will go here. And what's the tag? The tag will be 1 and a lot of ones and then followed by 3 zeros. That's the tag. Now, this was a miss too. So we have 3 values put in our cache. Now 011, 011. None of the cache indexes matches, so it will be a miss definitely. And 4 will go into 011, so 4 goes here. Okay. And then the tag is note the tag and also the index has to match. So just matching the tag won't help. The fifth one. Fifth one is 000. Does the cache, does it match anywhere? No, it's a miss. What's the tag? It's some zeros and then 1101. That's the tag. And it doesn't match with anything. It doesn't matter. First, the cache index has to match. And this one, it's, so did we put 5 in? No, we didn't. So let's put 5 in. 5 has to put in 000. Let's put 6. The thing is 100. Now we know we have 2 blocks, right? 2 blocks inside a set because it's a two-way cache. So we don't have to evict the thing which is in 100. We don't have to evict 1, right? Because there are 2 spots. So this 6 will be placed in the second spot because the tag number doesn't match. 111 0 1101. Now the final one, the cache index is 100 and the tag is all 0. So 100, okay, we find it. We found a matching one, and now does the tag match? Yes, it does. Both the tag and the cache index match. It's a hit. Now this wouldn't be a hit if this one was removed by 6, remember? But because we have space for to put in another location, that's why it's a hit. And note that these values don't have to exactly match to be a hit because all of the offsets are like all of the combination of the offsets 0001 1011 are gathered when you are gathering one memory location. So when you get one location, you get its buddies too. And then if you happen to, if that location stays in the cache and you happen to re-access that exact value or its friends, right? Or its friends, 0011 is in the same index. Also 00, oh, 0011. Like even if this binary value, if it was 11 at the end, still it would have been a hit because that buddy is inside this block because this block has 4 locations. Okay, it has a 00011011, and that's why it's a hit. And you don't have to put 7 inside anywhere because 1 already contains 7. So this is the second problem that is solved, and we'll do the last problem now. Again, the same process. We are canceling out the solution. And here it's a fully associated block, which means that they don't have any specific place to go. They can go anywhere which is available. Okay. So uh, so this is the final problem, and it's the fully associative cache. And here, you don't have a designated place to put the value. So, so you put the value in the first location that you find empty. And in this case, we are going to remove values using the least recently used strategy. And here are the binary values. You know, the block size is 4 bytes. So 4 bytes. And so for 4 bytes, you have uh, an offset size of 2. So 2 to the power n equals to 4. So this is the offset size, offset. And then the cache block, it gets determined the first available spot. So the first thing will go in the first available spot 0, 0, which is B1, B0, which is 0, 0. So let's put the first thing here, 1. This is 1, okay? Okay. The next thing, the tag number will be 0, dot, 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 0, and then 1, 0, 0. Okay. Good. The next one, does the tag match? It has lots of zeros, but the final 3 digits are 111. It doesn't match, so it's a miss. And it gets put into another block, the next available block, which is 0, 1. So it just gets put into another place. But the last recently accessed or used will be removed first. So once we reach this 4 limit, then we have to throw away stuff. Okay. So right now, the last used is 1 because 2 is recently put in, 2 is recently used. Okay. Now let's look at 3. So for 3, it's 1, dot, 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 1. And then the value is 0, 0, 0, 1, 1, 0. Okay, the tag doesn't match with anyone, so it's a miss and it gets put into block 2. It gets put into block 2 and block 2 is 1, 1. So 3 gets, okay, the next one, 1D. Right, let's go. So we first have to check if the value matches with any of the tags because there's no index number here. So we only need to match the tags for the fully associative cache. It's 111. Oh, look here. These two match, right? So because these two match, this is a hit. Because this is a hit, 2 has been recently used. And so just point out that 2 has been recently used because we did not need to put 4 in because the value of 4 is already inside this block because we know the block has 4 bytes, 0, 0, 0, 1, 1, 0, 1, 1, and the 0, 1 has already 4 inside it. So we don't need to put 4 in. It's a hit. Now, the next one is, so we don't need to put it in. So I put dot, dot, dot here, okay? Because it's already inside. Now, the fifth one, 0, dot, 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 0, 1, 1, 0, 1, 0, 0, 0. We haven't seen something like this before, so it's a miss. And it gets put into B3 or our last location, which is empty. Oh, this is 1, 1. This is 1, 0. 1, 1. 0, 0. This is 0, 1, 1, 0, 1, 1. Okay. Now 5 gets put in here, which is a miss. Okay, so 5 is a miss. It gets put in here. Now let's do 6. So 6, the value is 111 dot. No dots. 1101. This has been never given before. and it's a therefore it's a miss. There's no matching tags. Now all the locations are filled. Okay. Now what do? We have to follow the least recently used strategy. One was the oldest, right? And one never has been used. So one has to go. One gets replaced by 6. Now 7. So this looks like matching. Oh, it should have matched with 1, but 1 just went away. So it won't hit. It's going to be a miss. So we put this in B0, which is 0, 0, and we kicked out 1. And now this is going to be 0, dot, 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 1 and 2 zeros. It does match, but 1 has been kicked out. So this won't be a hit. It's going to be a miss. And where would we put it? We can't put it with 2 because 2 has been recently accessed by 4, like because we recently used 2, so we have to kick out 3 because 3 was like the oldest and not used. So so if we have to remove another one, then 2 will be removed because 5 happened after 4. So recently used is 5, right? So if we needed to delete the next one, then we would remove 2, but not now because after 3 to access 4, 2 has been used. Okay, so then remove 3 and put in 7. So that's the answer to this question. I hope you understood it properly, and these questions are really important for the finals. Thank you.